Welcome to class, everyone. I am absolutely thrilled to have you here for today's explainer. Look, we're going to take the complex, sometimes kind of intimidating magic of neural network training and break it down into simple, everyday concepts. Think of me as your guide or, your wildly enthusiastic professor ready to demystify exactly how these networks actually learn. If you've ever wondered what's really happening under the hood of modern AI, well, you're in the exact right place. Let's get into it. All right, so here's our syllabus for today. First, the first artificial neurons. 2, the forward pass and making predictions. 3, calculating the prediction error. 4, back propagation, fixing that error. 5, learning rates and Python. And finally, early versus modern networks. Let's jump in.
Okay, Section 1, the first artificial neurons.
Now, Arthur Samuel actually defined machine learning way back in 1959, and this brilliantly illustrates that the dream of teaching computers to learn entirely on their own, without us having to hard-code every single little rule, is a pursuit that's been captivating scientists for decades. I mean, it's not just some modern fad, right? It's literally a multi-generational scientific quest. And you know the heavy, intimidating math of modern AI? It's actually rooted in human biology. Back in 1943, McCulloch and Pitts really just wanted to mimic how biological brain cells, our neurons, fire. Then, by 1957, Frank Rosenblatt took that biological inspiration and created the perceptron. This was the first algorithmically described learning rule. And shortly after that, Wittero and Hopf introduced the Adaline, which swapped out simple binary switches for continuous linear math. That seemingly tiny shift, that laid the absolute mathematical foundation for the neural networks we use today.
Moving on to Section 2. Forward pass, making predictions.
So this is the golden question, right? How exactly does a network look at a bunch of data and actually make a prediction? What are the mechanical, step-by-step actions happening inside that black box? Well, let's trace the signal. Now, don't let the math here scare you. It's actually incredibly intuitive. Imagine you have two inputs, say the numbers 2 and 3 sitting there on the far left. Those inputs travel along those connecting lines to the next layer. But as they travel, they're multiplied by what we call weights. I always like to think of weights like the volume dials on a radio. The network basically turns the dial up or down on certain inputs depending on how important they are. It multiplies the inputs by these dials, adds them all up, and pushes the signal forward. And this exact process, that's called the forward pass. It's literally just a sequence of inputs being multiplied by weights and passed forward layer by layer until it pops out a final answer. In our example here, all that underlying matrix multiplication gives us a final predicted value of 0.191. Next up, Section 3, calculating the prediction error.
Okay, so here's the reality check. Our network confidently predicted 0.191, but out in the real world, the actual target value we were hoping for was 1.0. So we're way off. What do? We calculate the error. We find the difference between our prediction and the actual target, and then we square it. We do this partly just to make sure our error is always a positive number. In this case, our squared error formula tells us we have an error rate of 0.327.
Section 4, back propagation, fixing the error.
So the absolutely crucial point is this. We obviously want to reduce our error. But what can we actually change to make that happen? The inputs are fixed, the data is the data, right? And the target output is fixed because reality is reality. By decomposing the math, we realize the only variables we actually control are those weights, those radio dials we talked about earlier. To fix our error, we have to send a signal backward through the network to tweak those internal dials. This backward communication is what we call back propagation. Now, to know exactly which way to turn those dials, we use an algorithm called gradient descent. Picture this. Imagine you're blindfolded, standing on the side of a really steep hill, and your goal is to find the absolute lowest point in the valley, which represents zero error. You feel the slope of the ground with your foot, and you take a step in the direction that goes down. You just keep feeling the slope, taking step after step downwards until the ground eventually levels out. That is exactly what gradient descent does mathematically to those weights.
All right, Section 5, learning rates in Python.
So, think back to our blindfolded hiker for a second. How big of a step should they actually take? That step size is what we call the learning rate. If you set a really high learning rate, your hiker takes giant, reckless leaps. They might actually jump right over the bottom of the valley and end up higher on the other side. Not good. But if you set a very low learning rate, they take tiny, agonizingly slow baby steps, which takes forever and might leave them trapped in a shallow local dip. Finding that perfect, balanced step size is essential for your model to learn efficiently and converge on the right answer.
Now, when you're ready to code this yourself, you'll use a classic learning loop. Step 1, initialize your weights to random small numbers. Step 2, code a forward pass to calculate your output value. And Step 3, run your backpropagation function to calculate the error and update all your weights simultaneously. Then you just rinse and repeat that loop.
A quick tip as you write your Python script, you'll definitely want to use the NumPy library. Because you're dealing with massive matrices of data, you need to avoid standard Python for loops. They will literally take ages. Instead, use NumPy's vectorization features, like np-dot, to perform your matrix multiplications all at once. It's kind of the secret sauce that makes training these networks computationally feasible and incredibly fast on modern hardware.
Finally, Section 6, Early versus Modern Networks.
You know, the early grain-inspired models, like those first perceptrons, were actually quite rigid. They used binary, all-or-nothing step functions. They fired or they didn't. Simple as that. Because of this, they completely failed at solving complex, nonlinear problems. But modern networks, really starting with the Adeline we mentioned earlier, use continuous, smooth mathematical functions. And this is huge because it allows for gradient descent, our blindfolded hiker, to smoothly navigate complex multi-layered architectures, entirely unlocking the ability to recognize incredibly complex patterns in text, images, and sound.
Which leaves us with this pretty incredible thought to ponder. Every massive, world-changing AI model you read about today is fundamentally built on the exact same principles we just covered: forward passes, calculating errors, and walking down a mathematical hill to update tiny dials. If these simple mathematical rules, inspired by biology way back in the 1940s, can give us the AI we have today, what on earth will they unlock tomorrow? Thank you so much for joining me for this explainer. Class dismissed.